In this video, we are going to define and calculate relative humidity. Now, you'll recall from previous chapters that all the gases in the atmosphere have a weight, and that weight pushes down on the surface, exerting what we call a pressure. Pressure being defined as force per area, in this case, the force being weight. And you'll also recall that the total pressure that we experience is 1013.25 millibars, which we often just approximate as 1000 millibars. Okay, so that's the total pressure of all the gases on the surface. However, would it not stand to reason that a fraction of that pressure is being exerted by just nitrogen? If we got rid of all the gases except for nitrogens, then those nitrogens would exert a pressure on the surface of the Earth. So pressure due to nitrogen, since nitrogen makes up about 78% of the atmosphere, that would be about 780 millibars. Now, oxygen, if we calculate all the oxygen, remember that's about 20%. So the pressure exerted by oxygen comes up to about 200 millibars. And so on. You do this for every single molecule. Eventually, you do it for all the molecules. If you add up all the pressures by the individual molecules, it should add back up to roughly 1000 millibars. If we have exactly one standard atmospheric pressure, then it should add up to 1013.25 millibars. Now, along with all those other molecules, we have water. So the water that's in the atmosphere also exerts a pressure. So there is a pressure exerted by water. This pressure is vapor pressure, the pressure exerted by water vapor molecules in an air parcel. So let's say that 1% of the atmosphere is currently made of water. That number varies between 0 and 4%, but let's just say for argument, currently it's about 1% of the atmosphere. Then 1% of 1000 millibars gives you 10 millibars. So we would be feeling 10 millibars of pressure just because of water vapor. The more water molecules are in the air, the higher the vapor pressure is going to be. Now there's a limit to how much water the air can hold. This is the saturation point. Now here's an easy way to think of the saturation point. Think of the atmosphere like a jar. You could start putting water into the atmosphere or into your jar, and then eventually your jar will fill up. As soon as you reach the opening, the jar is 100% full. Any more water you put in will then spill out. The atmosphere is just like that. You start putting water vapor into the air will hold that water vapor until it reaches the saturation point, in which case it's going to have to start taking some of those water molecules, condensing them, and they'll just spill out of the atmosphere or rain, precipitate. Now, the amount of water that the air can hold, also known as the saturation vapor pressure, depends on the air temperature. The hotter it is outside, the larger your saturation vapor pressure is. Or using our analogy, the higher the temperature, the larger the jar. Here's a graph from your book that shows what the saturation vapor pressure would be based on temperature. So let's just do a quick example. Let's say that outside right now it is 86 degrees Fahrenheit. Then we find 86 degrees Fahrenheit on the graph, and then find what the vapor pressure is at that point. That is our saturation vapor pressure. In other words, that's how much water we can hold. In this example, we can hold up to, that's about 42 millibars of water vapor pressure. Now, how much we can hold is not the same as how much we actually have. It's like taking a jar and filling it only part way. We still have a capacity to fill a quart, but we only have a cup or 3 cups of water in a jar. So how much water is actually in the jar would be your actual amount of water. The amount of water vapor actually in the air is our actual vapor pressure. Now, this number we can determine by what we call the dew point temperature. Basically, the basic idea of the dew point temperature is if you take the temperature and you decrease it, in other words, decrease the size of this jar, until the size of the jar matches the amount of water we have, that is the saturation. The air would be saturated at that point based on the current amount of water in the air, and dew would start to form. So this is the dew point temperature. So come back to this graph. So we saw that the saturation vapor pressure was about 42 millibars. But let's say that currently, instead of having 42, we actually take a measurement and we have, about 12 millibars worth of water vapor in the air. Then that means that we have a dew point of 50 degrees. Given that amount of water, if the temperature were to drop down to 50 degrees, the capacity of water, so temperature drops to 50, then the capacity of water would also drop, and then we would become completely saturated. Once we hit that point, dew would start to form. So in summary, saturation vapor pressure is how much water the atmosphere can hold, the capacity of water. And that's measured by the actual temperature. Whereas actual vapor pressure is how much water is currently in the atmosphere. And that's measured by what we call the dew point temperature. Now, the relative humidity is the ratio between these two. So we saw here that the actual vapor pressure from this graph was about 12 millibars, while the atmosphere has a capacity of about 42 millibars. So relative humidity would be the ratio of actual vapor pressure to saturation vapor pressure times 100%. So actual we saw was 12 millibars, saturation was 42 millibars. Turning to my calculator quickly, 12 divided by 42 times 100% gives me 28.57%. That is the relative humidity. Okay, let's do one more example. Let's actually look at the current conditions here in Daytona Beach and find the current relative humidity. Okay, so here is a web page from the National Weather Service showing current conditions. Let me just go ahead and refresh this in case the numbers have changed at all, which it looks like it hasn't. So according to this, the current temperature is 78 degrees Fahrenheit. And if you look in the column just right of that, you'll find dew point marked as 75 degrees Fahrenheit. Now, we could convert these into Celsius. Let's just go ahead and use the numbers that are given here, 26 degrees Celsius and 24. So let me come back here and go ahead and write that the actual temperature, 78 degrees Fahrenheit or 26 degrees Celsius. And the dew point temperature, that's not written very well. Let me try that again. A little better. We saw was 75 degrees Fahrenheit or 24 degrees Celsius. Okay, from this information, now we need to find from the actual temperature the saturation vapor pressure, and then from the dew point temperature, we need to find the actual vapor pressure. So let's go to your Falcon Online. If you go to the content page under segment 1, chapter 4, you will see a vapor pressure calculator. This is a really nice module that I created for your purpose here in the class. If I open this up, it gives a nice saturation vapor pressure graph based on temperature. But if we move our mouse over the line, you can see that it actually gives us actual numbers. Well, it's supposed to, it's not coming up very clearly. But we saw that the actual temperature was 26. There we go, now it's coming out clear. So you see the temperature in the top left corner of this, of the box. So I'm going to move up until it says 26. Oh, passed up. There it is. So 26.0 gives us a vapor pressure of 33.62 millibars. So the actual temperature is 26. Saturation vapor pressure is 33.62 millibars. Now we need to do the same thing for the dew point temperature, 24 degrees Celsius. So I just move the mouse down. There's 24 degrees Celsius. Gives me a vapor pressure of 29.85. Then the relative humidity is just the ratio of actual vapor pressure, so 29.85 millibars, divided by the saturation, 33.62 millibars, times 100%. Now, turning to my calculator again, 29.85 divided by 33.62 times 100% gives me 88.79%. Roughly 89%. Now let's go back to what the National Weather Service page says. They say it's 90%. Likely the errors we had were in the fact that this 26 degrees Celsius was rounded. If I actually convert 78 degrees from Fahrenheit to Celsius, that number should have been 25.56. Close, but because of the rounding, our answer came a little bit off. That's okay. That's a good calculation of the current relative humidity in our area.